Hello, this is Teach Nichols, and this video is kind of a catch-all for a few little concepts that didn't make their way into other videos for kids that miss class when we go through it. The essential question is, what are some other useful or common situations or concepts to understand? So for starters, a little bit more about voltmeters and ammeters. Of course, remember that an ammeter measures current. And we talked earlier about where you put an ammeter, which is in series with the device you're interested in measuring the current for. But the pragmatic reason for this is because it's essentially counting the electrons that are passing through that device, because we know the junction rule says however many electrons go through the device have to go through the ammeter. If you had it in parallel, it would not actually be getting the same amount of current as the resistor would, and therefore wouldn't be a useful device. Along the same lines, ammeters need to be low resistance, because if they were a high resistance, they would actually reduce the current in the entire circuit or in the resistor that you're trying to measure. So ammeters are negligibly resistant. They're very low resistant devices that count the electrons. Voltmeters, on the flip side, are always going to be wired in parallel with your load. And the reason is because what a voltmeter actually measures is the potential difference from one side to the other. How much the energy changes from one side of a resistor to the other. You may remember that whenever two devices are in parallel, they have the same potential difference because they're part of two different loops, and therefore the electrons have to drop energy the same amount, whichever resistor they go through. So voltmeters always wired in parallel. Voltmeters, on the flip side, have to have very high resistances, because if they had low resistance, you would still be able to measure the potential difference, but they would be basically taking the vast majority of the current in the circuit instead of letting that current go through the load. And fundamentally, we want the meter, the thing that we're using to measure something, not to impact the function of the actual circuit. So voltmeters are high resistance and wired in parallel. Sometimes you get a problem in an exam where you're asked to talk about what does the voltage look like from one side of a switch to the other. If you have an open switch in a circuit, like in the circuit shown to the left, there's not going to be any current, obviously, flowing through those switches because the electrons can't get from one side to the other. And if there's no current through that switch, that means there's actually no current through those bulbs either. All right, the electrons aren't flowing through the bulbs. So in other words, there is no place for those electrons to use their energy. They're not going to drop voltage or use energy in the bulbs because they're not passing through the bulbs. They're just kind of sitting there. There is no voltage drop through any resistor unless there is current. If you think about Ohm's law, if I is 0, R is not 0, R's got a value, but if I is 0, then voltage is also going to be 0. So if you think about that in the context of this circuit, we know the battery has a voltage difference from one side to the other, and none of that energy is used up in the light bulbs. Therefore, there actually is a potential difference across the switch. The top side of the switch basically is the same voltage as the top of the battery, and the left side, and the right side of the switch is going to be the same voltage as the bottom of the battery. The potential difference across the switch is actually equal to the battery voltage if that switch is open. If you close that switch, things are different. Now we have current flowing through the resistors, and that means that the voltage drop in the circuit, the energy is used up as those electrons pass through the resistors. I say most because it depends whether we're talking about an ideal circuit with wires with no resistance or not. But in any case, the lion's share of that voltage is dropped across the bulbs or the loads in the circuit. Therefore, there is no potential difference across a wire. It's essentially a closed switch is the same as a solid wire, and if you measure the voltage using a voltmeter at two places on the same wire, you get 0 because the delta V, or the potential difference, is 0. So sometimes we see these problems. I call them sometimes dangling wires or dangling resistors. Because they're not actually functioning, they're not actually turning on, and you should realize that you might have a voltage difference across a gap in a wire based on the fact that energy is different from one side to the other. Another concept that comes up on the AP test regularly is something known as EMF. EMF sometimes labeled with this kind of cursive E, is just another synonym for the voltage provided by a battery. So I probably should have shared that when I defined the voltage variable earlier in the year. And another concept that pops up is something known as internal resistance. Internal resistance is often labeled little r when you see it in a diagram, and it's a characteristic of a real battery. So in an ideal world, the battery allows current to flow through the circuit, and there's no resistance in the wires, there's no resistance in the battery, so the load or the resistor gets to use all of the energy. But in the actual world, there actually is some resistance inside the battery as well. That's this internal resistance. You should know this because when you use a battery, it heats up, right? That energy is costing the circuit energy. It's taking some of the electrical energy stored in the battery and turning it into heat as the electrons flow through the battery. So when you're handling this real world scenario with real batteries, you basically would draw in your circuit diagram the cells of the battery like we've seen before with a positive side and a negative side, and then you kind of add another little resistor, usually labeled little r, in series with the wire that's coming out of the battery. So when you are doing calculations in your circuit, if there is internal resistance, you have to basically add another very small but non-negligible resistor in series. Okay, so the essential question, of course, was what are some of the other useful and common situations or concepts to understand? Hopefully, if you see one of these come up, it'll be familiar. Thanks for watching.